Sir, should I show the waveform?
You want me to show the waveform? Fine. 1 minute. I will just scroll up. I will go to my this one. Yeah, you want me to stop presentation, no?
No, sir, it's okay. You can keep.
You can, okay. Yeah, you can present, eh? Yeah, just okay. But you have shown more number of cycles even when m of t is negative, no? For negative peak also. For negative peak, the number of cycles should be minimum. For positive peak, the number of cycles should be maximum. Okay, F max and F minimum you have to show, na? Is it F? You have shown both maximum, right? Yeah, that is F max. And this one is also you are showing F. Oh, okay, it is correspond to F minimum. This F max again you are showing for next cycle. Okay, your voice is not audible. Fine, ma. Yes.
So this
Yeah.
check for one cycle.
Okay, okay, fine. Yeah, what about others? Others have written?
Sir,
Yeah.
sir, I tried, sir, but I did not know how to proceed. Can you show, sir, once?
Yeah, I will show now.
Yes, sir.
Yes, okay. 3 students have responded. What about others? Yes, what about others? So don't want to do any homework. Yes, Sagar has responded. Naureen and Prajwal says I could not find how to draw it. Fine. So rest. Rest will be rested. Yes, no try only.
So even I tried, but then I couldn't get
No,
some.
you tried, but even then you could not. Okay. What about Leah, Namita, Karunya? No try only.
Sir, I didn't get it, sir.
You didn't get it. Oh.
Sir, I did till frequency modulated wave, sir. Phase modulated, I didn't understand.
Okay. Okay, let me draw. So this is the M of t signal I have drawn, right? So with respect to this, let me draw. So you can draw the unmodulated carrier frequency also. Okay, so unmodulated carrier frequency will have constant amplitude, frequency, and phase. You draw that by yourself. Okay, I will draw directly the frequency modulated signal. I hope everybody understood now what to draw. Draw by yourself the unmodulated carrier frequency. Okay, this is time. See, this is the maximum amplitude of the message signal, right? This portion is the maximum amplitude of the message signal. So at this point of time, see, what is FM? How do we define FM? Yes, how do we define FM? Yes, someone can answer, na? I'm asking.
Sir, the instantaneous frequency of carrier is modulated by message signal.
Means as M of t. See, deviation also we have told delta f. That is the frequency deviation, right? So what is the expression for delta f? It is kf into, yes, kf into
Maximum of message signal, sir.
kf into am, right? Where am is the amplitude of the message signal. Means the frequency of the frequency modulated signal is proportional to the amplitude of the message signal, okay, and it is independent of the frequency of the modulating signal or message signal, we say. Okay, so frequency deviation is what is the maximum change in the frequency of the carrier signal, that is of frequency modulated from its unmodulated value. That is the frequency deviation, right? So here M of t is maximum, no? So we expect more number of cycles in this duration. Okay, so this is the maximum frequency for FM, what we can say. For FM, at this point of time, there will be maximum frequency. This is positive peak, right? And similarly, so this is the negative peak of the message signal, right? During this period, so we can expect, because it is reducing, right? Amplitude of the message signal is reducing. So at this instant of time, we need to draw less number of cycles. So here, this will be FM minimum frequency. Okay. And we can draw a line to say that the envelope, okay, or so it is constant, okay. When compared to amplitude modulation, there the information resides in the envelope of the modulated signal, right? Here the envelope means the carrier amplitude is constant, okay. So at this point of time, it oscillates at the unmodulated carrier frequency, okay. So here we say it is F minimum. Like this, okay. So what I said, this part, we are finding it F max, okay. And this portion, we say it is F minimum. Yes, is this fine? Yes, is this fine? I am asking. When the amplitude of the message signal is maximum, during that time, there will be a maximum. Means more number of cycles per second will be there in the frequency modulated signal. Okay, when amplitude of the message signal is negative peak, so there less number of cycles will be there. This we call as the F minimum. and at other point of time, okay, for other point of time, the frequency of the modulated signal FM will be equal to the unmodulated carrier frequency. I'm saying just portion, okay, I'm showing this portion, other portion of the message signal duration. Here it will be an unmodulated carrier frequency, this portion, okay. And even another question also. So now let me draw the PMU, that is phase modulated signal. So what I said, what is phase modulation? Yes, what is phase modulation?
Phase of the carrier is modulated by message.
So can
Yeah,
you scroll?
the phase of the carrier is proportional to message signal.
So,
Question, theta I of t is equal to what?
sir?
What is theta I of t? Yeah.
So can you scroll on top, sir? Just copy that.
I will draw. Yeah. Yeah, here you can redraw this one with the number of cycles, okay? So you want to find the difference here in this duration, how many cycles are there? 1, 2, almost 2.5 cycles. Here I have written only 1 cycle, right? So this is F max and this is F minimum. Yes, use it written. This is the FM wave. And this we call as envelope. So envelope is constant here, right? Yeah, as I said, the frequency is what? The derivative of the phase for phase modulation at this point of time. Okay. At this is the increasing amplitude, right? From this point, the amplitude of the message signal starts increasing, right? So at this point, okay, at this point for PM, okay, for PM, there will be maximum frequency. Because I said why, right? Because we derivative, right? We differentiate and equate it to 0, no? To say it is maximum, right? Because of that. Okay, and here at this point, see it is here it is a positive going amplitude, right? Again for this point it is going negative going amplitude, right? At this point there will be F minimum. Okay, so for this at this point of time for PM there will be a minimum frequency. Okay, for rest of the thing it will be as good as the unmodulated carrier frequency. Okay.
Sir, can you scroll a bit more, sir? I cannot see the top part.
For message signal.
Yeah, thank you.
So for rest of the things, okay, means at this point of time for PM, okay, for phase modulation, I say the frequency will be equal to the unmodulated carrier frequency. Okay, even for this point of time also. I hope you are able to find the difference now between PM and FM. Yes, able to find the difference. Yes, shall I scroll down?
So just a minute.
Huh?
Just a minute, sir. We'll copy.
Yes, sir. Shall I scroll down?
Yes, sir.
So this point is important for me because it is zero crossing, right? And this is also. So I need to show more number of cycles at this point. Then it will be what, as good as the unmodulated carrier frequency, right, at this point of time, right? And here it will be again F minimum it is. Then after that again it will be unmodulated carrier frequency. And all this. Okay. So at this point of time we'll get F max for PM, and at this point of time we'll get F minimum. And we say the envelope is constant. And this is the PM wave. I hope it is clear where it will be F max and where it will be F minimum with respect to the message signal for PM wave.
Yes, sir.
Okay. Now let us try to find out the relationship between FM and PM. Okay. I hope noted this waveform.
1 second, sir.
Yeah, looking at the waveform of PM and FM, is it possible to visualize where the message signal resides? Like as that of AM, it is easy to visualize now because the message signal will be there in the envelope of the modulated signal, right? But looking at the waveform of FM and PM, is it possible to visualize the message signal in the modulated signal? Yes, able to get that visualization?
Yes, sir.
No, man. How we will be able to visualize, man? How we will be able to visualize? Is it so easy to visualize as compared to AM? In AM, it is very clear, right? The envelope of the modulated signal resembles the shape of the modulating signal. That is the message signal, right? But here, looking at the waveform of either FM or PM, you will not be able to visualize the message signal. Okay, what will be its shape and all. So that is why we say it is a non-linear modulation. Okay, AM and its variants are the linear modulation. Do you know what is linear and non-linear? Yes, linear and non-linear. When do you say it is linear? Yes, to say linear, it should follow what? Or it should obey what? Linearity, man.
Sir, it should be proportional.
No. I will talk about linear. See, if it obeys the principle of superposition, right? Then we say the system is linear. Okay, if it is not obeying the principle of superposition, then we say it is a non-linear. So FM and PM, or we say angle modulation, is a non-linear modulation. I will come to that when the frequency of the carrier is modulated by m of t, what we get. When it is modulated by two different sets of m of t, so what we get. Then when we combine and do it the modulation, is it the same or not? Okay. So before going to that, let me just try to establish the relationship between FM and PM. Okay. Relationship between FM and PM. Yeah, to understand how FM and PM are related, okay, so let me write the expression for PM and FM. Yes, so Danya, can you say what is the expression I can write for PM, the PM modulated signal?
Yes, sir.
Yeah.
S of t is equal to?
Yeah, S of t. Let me write the suffix as PM to say it is a phase modulated signal. Yes.
AC cos 2 pi
Yeah.
FC plus
Yes, AC cosine of
2 pi FCT plus KPM of t.
yeah 2 pi FCT plus KP into M of t, right? Let me call this as equation 1. Yes, Karuna, can you say what is the expression for FM? Karuna? Yes, I'm asking Karunya.
Hello, sir, can you hear me?
Yeah, I'm able to hear you. Yeah, can you tell the expression for FM?
FC plus KFAM
Frequency
cos
modulated
2 pi
signal.
FMT.
Frequency modulated signal. Yes, how we have written for PM in the same fashion. What is the difference? Will be AC.
You'll have KF.
You are not familiar with the equation only, I think. Right? Yes or no? It shows you are not studying because you don't know basic equation. This has been taught in the previous class also. AC cosine of 2 pi FCT. Yes, next is the difference. What is the difference?
KF, sir.
It is just KF or 2 pi KF?
2 pi KF.
Then what? Is it M of t or integral of M of t?
Integral M of t.
So 0 to t, right? M of tau into d tau. Let me call this as equation 2. Yes, all of you observe these two equations. And is it possible to say the difference? in what way they are different and in what way they are similar. Just take 1 minute time, observe and see, is it possible to obtain FM signal from PM signal? Similarly, PM signal from FM signal, you should be able to tell. Looking at the expressions of these two equations.
Sir,
Yeah.
sir, by looking, like first look, we feel that KP should be the same as 2 pi KF.
Okay.
And M of
And that
T
is
should be
constant.
same
Don't worry
as
about that. Okay. Then next, what is change?
M of T should be same as 0 to T M of tau d tau.
Yeah. Means if I replace m of t, right, in the equation 1 with the integral 0 to t m of tau into d tau, right? So what I get?
Yes.
Yes, it changes pm into fm, no?
Sir, what about the 2 pi KF and KP,
That
sir?
is constant only, no, man. This is a phase sensitivity and this is the frequency sensitivity. It's a constant.
Oh, it's constant means, yes, sir, correct. Sir.
Ah. So if I replace m of t in equation 1 by integral of what? 0 to t m of tau into d tau, can I say this pm changes into fm? Is it possible to say we can change phase modulated signal into a frequency modulated signal? You can't say. I'm asking if I replace m of t in this equation 1. Yeah. By what? By integral of 0 to t m of tau into d tau. Then can I say the PM is changed into FM? Means phase modulated signal is changed into FM signal?
Yes, sir.
Yes, what about others? Only one or two saying yes, sir.
So,
Yeah.
so the S of Fm of t,
Yeah.
the equation should be AC into cos of 2 pi FCT plus KF into integral of m of tau d tau, right?
That is what, man, I'm replacing. See, this is constant, I said. No, Kp and 2 pi Kf is constant only. Okay. Just I'm talking about the m of t replacing. If I replace this m of t in the equation 1 by this term, integral of this, can I say changes Pm into Fm?
Yeah, sir.
You should write and then you will be able to understand.
No, but then sir, 2 pi doesn't exist.
M of t, replacing m of t in equation 1 by the integral of what? 0 to t m of tau into d tau. Can I say the phase modulated signal changes into frequency modulated signal? And leave this term, this is a constant term only, no, Kp and 2 pi Kf.
Yes, sir.
You have to substitute and see. Then only you will understand, I feel. Just saying in words, I think you will not. I said replace m of t in equation 1 by what term? By the integral 0 to t m of tau into d tau. Okay, that changes the phase modulated signal into a frequency modulated signal. Keeping this constant in mind, that means you can replace Kp by 2 pi Kf. Yes or no?
Yes, sir.
Yeah, this is the third candidate saying yes. What about others? Still another 53 are there, no? 53 or 54. Able to understand what I am saying? I have written two equations, one for PM, another for FM. I am just comparing those two and I am saying the term m of t, if I replace in equation 1 by what? Integral of 0 to t m of tau into d tau. Can I say I can change the phase modulated signal into a frequency modulated signal? So replacement is not possible, na? It is not going. Yes?
Yes, sir, we can.
Yeah, we can, no? Okay. Similar to that, what we can do, we will be able to replace what? Let me draw the first one, I think. Let me clear one by one. So what I said, let me write here m of t, okay? If this m of t okay, m of t is applied to an integrator. Okay, then what I get here, integral m of tau into d tau, right? M of tau into d tau. If I apply this signal as input to the phase modulator, okay, PM here is not product modulator, it is a phase modulator. Then I can say I'll be able to get the FM signal. Is this fine?
Yes, sir.
Yes, sir.
Frequency modulator it is. Okay. Means a signal that is an FM wave, right? Corresponding to what? This M of T, right? Is also the phase modulated wave, right? Corresponding to what? Corresponding to integral of M of tau into d tau. See, this is the phase modulator I said, right? Means why I have written a dotted box here to say that what I said, a signal that is an FM wave corresponding to what? This message signal M of t is also what I said, the PM wave corresponding to what signal? Corresponding to the integral of M of tau into d tau. Right? So similar to that, we can write the another block that is for saying phase modulation. I hope you noted this diagram. Yes, is it noted?
Yes, sir.
Yes, sir.
So now let me say in the same fashion, m of t, okay, yes, Pm of t I get here. Okay. Yeah, now you should be able to tell what should be written here inside the box.
Differentiation, sir.
Yeah. So the first block should be what? Means what is the understanding here? Similar to FM, what I said. What I said for FM, the signal that is an FM wave, right, corresponding to this message signal M of t is also what I said is a phase modulated wave for what input? For the integral of M of tau into d tau, right? In the same way, here the PM wave, okay, the signal PM wave corresponding to M of t is also what? D by, if I differentiate this message signal, right? Means if I use a differentiator here, what I get here? D by dt of M of t I get, right? D by dt of M of t. If this is the input to the frequency modulator, okay? Frequency modulator, right? So I will be able to find the frequency modulated signal for the derivative of the message signal, right? A signal which is FM for a signal what? For the input signal M of t is also is what? A signal FM wave for the derivative of message signal, right? So it is a little bit tricky to understand at the beginning. I am relating with respect to this, a signal FM, right? Just I am writing here, okay? So for, I'm saying what I'm saying, for M of t I get PM signal, right? With some block, right? What I'm doing here is I'm differentiating this message signal and I'm applying that as input to the phase frequency modulator. So output of the frequency modulator, what I get the frequency modulated signal, no? For what type of input signal? For the derivative of the message signal, isn't it? And that is also equal to what? The phase modulated signal. Similarly, in the upper block, what I said, the frequency modulated signal for the message signal M of t is also a phase modulated signal for what input? For the integral of M of t into dt. Okay. If I integrate and apply that as input to the phase modulator, I will get in the phase modulated signal that will be same as what? Frequency modulated signal. Hope understanding what I am saying. These two are the important blocks, how they are related. Yes. So just to give an analogy, because to understand this, it is as good as asking a married person, okay, having childrens, okay, asking whether you are a son or father. What he will say? Yes, what he will say? You didn't understand my analogy, I think. It is as good as asking a married person having a children, right, whether you are a father or a son. What he will be answering? What he will be answering?
Father.
Both, sir.
You are not understanding the sentence. I said it is asking a married person having children. Okay. For him, you are going to ask, are you a father or a son? What he will be able to say?
Both.
He is both, no, because he is father to his children and he is a son to his father. Yes or no? Yes or no?
Yes, sir.
Like that, here also, it is means highly impossible to separate, okay, FM from PM. So they are like that. I hope you could understand. Means PM and FM are similar. I wanted to convey that. Okay? I don't know how many of you could get that point. As far as angle modulation is concerned, okay, FM and PM are similar. Okay? That is why I given that example. Yes, is that clear? And how they are related also understood?
Yes, sir.
At least you should understand first analogy, na? Analogy, is it clear? What is analogy? Can you repeat? Anyone can repeat what I said? Other than this Kuber, Prajwal and Naurin, others should talk. think I will call with names. Yes, Chandana. Chandana.
Yes, sir.
Yeah. What is the analogy I've given, ma, to say how FM and PM are similar or they are different?
Person, sir, you gave that example.
Yeah. Can you repeat that example? I think you didn't get that example.
No, sir, I got that example.
Huh? Yeah. Can you repeat? I'm asking.
Asking a married person whether he is a father or son.
No. Asking a married person having children. Okay. Are you a father or a son? You people only said he is both, right? Because he is a son to his father and he is a father to his children. Okay. So that is how this FM and PM are interrelated. So it is inseparable. Okay. They are similar. Okay. That is why we deal only with the FM, not with the PM. All generation, detection, everything is similar to that. Fine? Yes, is this fine?
Yes, sir.
Yes, sir.
Okay, that is analogy to understand. What with respect to this, what if anyone can repeat just once?
So in the first,
Hmm.
to get an FM wave, what we do is the message signal. First, we integrate the message signal. Then we give that as the message signal to the PM modulator. We get FM. And in the second case, the message signal is differentiated, and that is given as a message signal to FM modulator to get the phase modulated signal.
Okay.
Yes, sir.
So means with respect to the dotted block I said, no, FM signal with respect to M of t, right, is also a phase modulated signal with respect to what input? I think you didn't get my point. I was talking about this. See, this is the frequency modulated signal, no? With respect to what input? With respect to the message signal M of t, right? Now,
yes, sir.
Yeah, it is also an FM PM signal with respect to what input? This input with respect to the integral of M of t into dt or M of tau into d tau. Yes or no?
Yes, sir.
Similarly, the second block, see, is a phase modulated signal with respect to input M of t. Okay. It is also a frequency modulated signal with respect to what? The differentiation of the message signal. Okay. So, this is what we say how the FM and PM are related. It is not a tricky also, it is very simple to understand, but replacing integral, replacing differentiation, people should understand this. Okay. Others are not speaking. I don't know their response, what it is. Yes, Ananta, can you say, man? What about Sagar? Could you understand what I said? Yeah, Bharati. Bharati.
Yes, sir, that's understood.
Understood. Why you left yesterday, man? As soon as I started asking questions. You joined?
No, sir, I didn't join. It's a power cut here.
No, yesterday you left no, immediately. The moment I started asking questions, you left. Like you, another 9 members are there. They're not responding.
No, sir, I didn't even join.
Okay.
Understood, sir, this one. Even the analogy.
Okay. What about Anand?
Yes, sir.
Yeah. Can you tell, man, how FM and PM are related, man? Not with the analogy, you tell with respect to the block. Anand.
Sir, they're interrelated, sir.
Yeah, how they are interrelated, you should tell. And quiz, okay. You can take up the quiz now. It will be over by 11:50.
Sir, in frequency modulator,
People
message
can
signal
thoroughly quiz also.
is integrated, whereas
Can
in phase modulator it is differentiated, sir.
Okay, you should be able to say how no, that is a signal that is an FM wave corresponding to the message signal M of t is also the phase modulated wave corresponding to the integral of M of tau into d tau. You should say in that manner. Okay.
Yes, sir. Yes, sir.
Similar to that, a PM wave corresponding to M of t is the frequency modulated wave corresponding to differentiation of message signal. Okay. Yeah, all can take the quiz. I given only 4 questions. Attempt. I hope I expect all. How many? 55 people are there. All 55 will take up and finish up. It will be over by 11:50. Okay. In the meantime, I think people can say the attendance.